Hi folks, this is the first video for Unit 1 Day 3 and we're looking at adding and subtracting vectors in this lesson. So first of all, we want to kind of think about why, because we will be looking at different applications of adding and subtracting vectors, but why this is something that we might want to be able to do. So a few kind of real life examples might be with travel, distance, direction, velocity. If you had vectors going in multiple directions, the resultant or the sum of those vectors would be sort of a summary of your start point to your end point. Another very common real life application of vectors is talking about forces that are working on an object. So if you had, say, a force pushing an object one way and a force of friction and force of gravity, by adding up all of the forces together, you end up getting a good picture of what's going to be happening with that object, whether it might be moving or accelerating or not, depending on what the sum of the different forces are. So those are a couple examples of why we might need to add vectors. So there's two basic ways, two types of diagrams that we're going to see in terms of adding vectors. The first one's called the triangle law of vector addition, and this is what I will mostly be using. The parallelogram law I will absolutely show you. I'm just going to make a note here that this is the most common. Because with the triangle diagrams, we're going to be able to use that trigonometry that we talked about and reviewed in the day one work. So the parallelogram law is actually very helpful for taking a look at how different vector addition problems work and whether you can add vectors in different orders. But generally, we're going to be looking at vector addition as a triangle. So in this diagram, and this is kind of one of the things that doesn't translate as well to video and paper and pencil as it would in an actual PowerPoint where I have animations for this. But if we have two vectors, vector v here and vector w here, we could find vector v plus w by translating the tail of w, so that's the starting of vector w, onto the head of vector v. So vector addition is always going to be head to tail. So I'm going to kind of try my best here to draw in vector v. Remember, vectors have magnitude, they have direction, but they don't have location. So this vector here, I can draw it anywhere on my page, and that's the same vector. Ish. I've gotten it pretty good there, I think. And then vector w in this direction will be like that. So the important thing to note here is that vector addition is always head to tail. So what I mean by that is that we have the tail of the first vector going to the head of that vector, and then we start there with the tail of the second vector. So they're kind of making a path, like vector v goes from here to here, and then starting at the end point of the first vector, we'll start the second vector and then go to the end point of the second. And the resultant vector, or the sum of those two vectors, goes from the beginning or the tail of the first vector to the head of the second vector. And that's going to work the same, as we'll see later on, with multiple vectors. If you were adding 3 or more, it would work the same way. So this is the really important thing, that you have to, when you're drawing these diagrams, draw one vector and then start the second vector at the end of the first vector. So once we've done that, we're going to have a triangle and be able to use all of our regular trigonometry. So all of the things that we were able to do with any kind of triangles, we can do with these. So we can figure out angles between these vectors. We can figure out the magnitude, often using the cosine law of that sum. Okay. The other thing, and I'm just going to kind of quickly redraw a rough diagram of, this is maybe a bit different angle than what I had before, but pretty close. So in the last slide, I had vector v and w, and then vector v plus w, this resultant vector there. Now, does the order matter? Can we put the tail of v to the head of w? And you'll find that we can. So if we had started with our w vector, and again, this isn't probably perfectly to scale, but hopefully you guys see and get the idea of it, and then put v at the end, so done w first and then v at the end, the resultant vector here, this sum, does end up the same. And this is a good kind of diagram showing what we're talking about when we talk about a parallelogram, is that if you kind of squeeze these two together, that these would form a parallelogram because these are equal and these are equal, the two v's on the side and the w on top and bottom, that this diagonal will be the same. So it basically that it does not matter what order you did this in, like there and then there, that these will be the same in either direction. So you can kind of make a parallelogram, and it might make it easier sometimes depending on the different angles that you might know. Okay, so this is just kind of a diagram of that again, that you can complete this parallelogram. You can draw in either the w at the end of the v or the v at the end of the w. I should have just waited for this slide, but that's okay. So here we see that that resultant vector is going to be the exact same no matter what order we do. Okay, so when we go to use our trig, we're only going to be looking at 1/2 of that parallelogram. So we'll be looking at the top triangle or the bottom triangle and using all of the regular trig rules that we know to calculate the magnitude and the direction of the resultant vector. Another definition here, the zero vector is a new kind of concept that we haven't talked about yet. And basically it's when two opposite vectors are added. So if you had, say, vector A, B going that way, and then a second vector BA, remember vectors have magnitude, direction, and not location. So this is the same as if I had drawn it right on top. But you can see that if you go from A to B and then add on from B to A, you get right back where you started. So you haven't gone anywhere. The magnitude of this sum is going to be 0. Now, if a vector has a magnitude of 0, it can't have a direction. It has nowhere to be pointing towards. So the only vector that exists that doesn't have a direction is this 0 vector. So its magnitude is 0 and its direction is undefined. And we just use the notation of a 0 with a vector sign on top to indicate that that's the 0 vector.